Welcome to Ask and Learn.
Right, we're going to define the positive y-axis as upwards in the direction of normal force. We're going to define the positive x-axis as uphill. And so this is the free body diagram for part A. And what happens here is that normal force of friction is acting downhill because the sled is going up and it's opposing it. So we resolve forces in the y direction. The net force is normal force minus vertical component of gravity, mg cosine theta, and that's equal to 0. So normal force is just mg cosine theta. So we know that force of friction is equal to normal force times mu k. So it's mu k mg cosine theta here. Therefore, we can do energy conservation. At the bottom, you have initially you have 1/2 mv1 squared, the initial speed. On top, you have the potential energy mg d sine theta, d sine theta being the height, and add to that the work done by friction, which mu k times mg times d cosine theta. So this is just force of friction times the distance, which is d. And so the g's can be canceled. You can take d common, d times g sine theta plus mu k g cosine theta is equal to 1/2 v1 squared. Therefore, d is v1 squared over 2g times sine theta plus mu k cosine theta. And then we plug in values. D equals v1 squared, which is 2.4 meters per second quantity squared, over 2 times 9.8 meters per second squared, times sine theta is 28, mu k 2.25 times cosine 28, giving us 0.43 meters approximately. In part B, the situation is just reversed in terms of friction force. Force of friction is acting upwards now, okay, in the positive x-axis, in the positive x direction. So therefore, we want force of friction to be less than the vertical component or the horizontal component of gravity. So mg sine theta is what that is. That has to be greater than the force of friction. So mg sine theta is greater than k mg cosine theta, because normal force is the same still. And so mg's cancel, and you pull cosine theta to the other side. Sine theta over cosine theta is tan theta, giving us mu sub k must be less than tan theta, which is, of course, tan 28. So we get here that mu sub k must be less than 0.53. All right, and finally in part C, we again do energy conservation, and the same for work done by friction applies, but initial energy at the top, you have gravitational potential energy, so that's mg times height d sine theta. That's equal to 1/2 mv2 squared, velocity that we're interested in, plus mu sub k mg d cosine theta again. So obviously the m's cancel, and v2 is just the square root of 2gd times sine theta minus mu k cosine theta. So plugging in values, you have 2 times 9.8 times 0.43, as we found in part A, times sine 28 minus 0.25 cosine 28, giving us a velocity of 1.4 meters per second.